Okay, hello everybody. Hello. Today's technical difficulty is brought to you by the CSE servers going down last night. So our website with the slides didn't get updated, so I've copied it across from my laptop. So thank you CSE, at least it's not the science theatre for now. We hope. Cool, so how are you all going? It's week 12. Don't panic, it's coming up next. It's been a pretty full-on semester, I think, for most of us, if not all of us. It's week 12. We're nearly there. That's sort of terrifying for you and for me. But, you know, we've got some cool things this week. We've got some super cool things next week. We've got a guest lecturer coming in, Richard Buckland, if any of you have heard of him. He's fantastic. So that'll be fantastic. And the Mandelbrot Art voting thing for the competition for that is now out. How many of you have voted so far? A couple of you. So definitely go look through them, vote for your favorite ones. The winner for that, the prize will be presented in Monday's lecture next week as well. So you want to be there for that. A couple more things. Assignment 2's in progress still. Hopefully you're working on that. Hopefully it's going well. I've been reading your progress blogs, those of you who've been writing them. They've been really good. Play.c is coming out this week, probably today, in fact. And don't forget to check Spots, the website that runs your game against everybody's tests and your tests against everybody's games. Cool. And so let's jump into linked lists. The things we worked on last week were mostly working with just a single linked list. But what if we had multiple lists? Like anything we can do with arrays, for example, we can do with linked lists and more. And sometimes we want to do things with more than one list at once. So a couple of examples. We could compare two lists, see if a list is the same as another list. We could combine two lists, so maybe we add one to the end, maybe we merge them together. We could append a list onto the other, or something like that. Zoom in. Yeah, how's that? Cool, and without further ado, let's do some coding. So hopefully everything will work on VLab. I know it wasn't working on one of the servers this morning. We'll have a look. So far, so good. Cool. That is not the right editor. Actually, Jishank used Emacs last week. I'll show you Vim. So the editor that I prefer to use is called Vim. It's an editor that you can use in the terminal, as is Emacs. There's a massive war, I guess, between people who use Emacs and people who use Vim. I think Vim's better. It's up to the person to decide what they like. This is a fairly boring file, but I can do things like, look, copy lines, look, delete lines. Everything's great. I recommend if you're feeling adventurous, play around with text editors. Try things like Vim, Emacs, Nano. There are other graphical ones like Sublime Text, I think is very good. There are probably some other Mac-specific ones that I don't know about, or Windows-specific ones. Okay, there we go. Here are some functions I prepared earlier, but not in the file that I thought they were in. So I've written some functions to get us started. One called newList that returns a list. One called newNode that makes a new node. MakeList, which makes a list, and PrintList, which prints a list. Very surprising, I know. So I'll quickly run through how these work. Hopefully you're pretty familiar with linked lists a bit by now. So the MakeList function makes a list. It starts out by making a new list, allocating memory, and then the list's head node is new node with the value 1. The one after that has the value 2. The one after that has the value 3, and so on. And we've done this without making any temporary variables or any other node pointers in the middle, because each node has a pointer to the next node that we can just go straight to. So that gives me a list. Allocating a new list, fairly straightforward. We allocate the memory. We make sure that it worked. Then we return the list we got. And a new node, similarly, allocate the memory, make sure it worked, set the value to the value we want, and then return. So let's do something with two lists. Let's go list first equals new list. Let's go list second equals new list. So are these lists going to be the same? I'm seeing one person nod and everybody else asleep. Yes, thank you. Very, very spoken. So what do we mean by the same? Are these lists going to be the same list as each other? Are they going to be two pointers to the one list in memory? Or are they going to be two separate lists in memory with the same values? The second one. Yes, so we're calling new list twice, and even though our lists, we have two lists with the same values, they're two separate things in memory, because each time we make a list, we make a node, and each of these allocates us a new piece of memory. What could I do if I wanted to make a new list that was actually the same as one of the lists here? What if I just went something like this? And so this is making me a capital L list, so a pointer to a list, called also first, and that is equal to first, which is the pointer to the other list, or the list we made. And so with this, anything that I did to the also first list would also change the first list, but anything that I did to the second list wouldn't change the first list. Cool. So let's write a function to see if two lists are equal. And for this, let's hash define incidentally, you can define true as 1, or you can define true as 1 equals 1, which is true by definition. It's not possible for this to not be true, because if 1 is equal to 1, which it is, then that's true. Or you can hash define them to 1 and 0, whatever you would like. So the logic here, if the two lists are equal, I'll put that up there, return true, otherwise return false. So there are steps, really easy, right? They're just going to go, if they're equal, return true, if they're not equal, return false. Program solve. But how do we actually check if two lists are equal? So given that we have a specification for a problem, or a thing saying to us, please do this thing, please solve this problem, please tell me if the lists are equal, what's the next step we need to do to determine if they are actually equal? Say that again? See if all of them are equal to all of them? I'm sorry, I can't hear well enough. I'm sure your answer was probably right. Yeah, so we need to check if two lists are equal, we need to compare the two lists. So a tip for things like the practical exams we have, the prac exams we have, especially for linked lists, but even for other ones, draw pictures. Drawing a picture on paper in the paper we give you in the exam is one of the most helpful things you can do. I've invigilated a lot of exams, so I'm the person who walks around being really bored, making sure you're not cheating. And the students who I see who start out by drawing a picture, maybe they spend 5-10 minutes on that, they then write the code up, they're done. Whereas the people who start coding straight away generally tend to write some code and then they have some bugs and they've got to find their bugs and then and so on. So let's make ourselves a list. And with the power of duplicating things, let's make ourselves another list. Unfortunately, your paper can't do that in the exams. It would be very nice. So as a human looking at this, it's pretty straightforward to go, these are the same, right? They have the same values, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But as a computer doing it, computers can't just sort of look at things and magically go, these things are equal, these things are not equal. they've got to go one slow step at a time through each thing. So what are the steps that we would do here? Make a while loop. Hold that thought. So you're jumping into implementation thoughts. He said make a while loop as a first step. But that's jumping straight into the implementation, and it can be good to, before we work out how to code it, work out how to solve the problem, sort of in bigger picture steps. So hold that thought. Did someone else say something? Yeah. Make two current pointer things. I'll abstract a little bit more because making current pointers is still a coding thing. Start out by looking at the first nodes in each list. Cool. If these nodes are equal, then what do we know? Is the list equal if these two nodes are equal? It's a good point. If their pointers are equal, are they equal? It's a good thing to think about. If the pointers to each of these nodes, if these both point to the same memory address, are the lists identical? Ever think about that? Yeah? Check if they have the same number of nodes. Cool, so one thing we could do is see if they have the same number of nodes. Why is that worth doing? Yeah, if they don't have the same number of nodes, they can't possibly be equal. And so we wouldn't have to keep checking each thing. So that's a good thought. Check if I'll write that down. Lengths are equal. But I have a question for you. How do you find the length of a list? Yeah, you go through each node until you hit the end and then it's null, right? So we'd have to go through every node anyway. If we had a way to get the length of a list in one step, like maybe if the list struct itself knew how long it was, then yes, that'd be a good first step. But otherwise, we can check the lengths as we go through and also compare the nodes. It's a good thought, though. Any other thoughts? Sorry, can you talk a bit louder? If they're identical or equal, we're checking if they have the same values. Yeah, if they're equal rather than identical. Yeah, so we have two linked lists that may or may not have the same values, but have different physical nodes in memory. Cool. So the question was, if the two first nodes both equal 1, is the list equal? I saw a no and a lot of silences. Easier question, if the two first nodes aren't the same, is the list equal? No, it's not equal, because they're not the same. I'll write this down. If the nodes are not equal, so if the two nodes aren't equal, then the lists can't be equal. We've hit a point where there's no way at this point that the lists could be equal. So we know for sure that it's not equal, so we can stop doing what we're doing. But if they are equal, what do we know? Yeah, it's possible that they're equal, but they may or may not be equal. So we've looked at our first nodes. Either they're equal, in which case, either they're not equal, in which case the lists aren't equal, or they're equal, in which case the lists might be equal. So then we need to check the next nodes, right? So now we would look at this one and this one. Are these ones equal? Yes, they are, so the lists might be equal. And so on, then we'd look at this one and this one, and this one and this one, and this one and this one. So these nodes are all equal all the way through. What about when we hit the null? What will we do at that point? Yeah, if they're both null and everything else before them have been equal, then they're definitely the same. Cool. So if they are equal, it might be equal list. Keep going. Cool. And so we've sort of worked out the strategy we're going to use, the algorithm we're going to use. Go through each node in each list. If the nodes are not equal, the lists aren't equal. If the nodes are equal, the lists might be equal. Okay, so we're going through each node in the list. For each node, if they're not equal, the lists definitely aren't equal. If they are equal, the lists might be equal. And then we want to keep going until we hit the end of the list. Okay, so how would we go about coding this? How do we go through each node in each list? Or how do we go through each node in one list? Yes, this is your moment of truth. Yeah, make a while loop. So while something, the best way to write code is to just put in something until you work out what it is and do the things you can do. So if the nodes are not equal, the lists aren't equal. We're going to need some way to compare so if the nodes are not equal, if current first something does not equal current second something, the lists are not equal. Okay, and else, if they are not equal, then they are equal. Then the list might be equal. Cool, so what's the thing we want to do in here? How do we check if the nodes are equal to each other? Yeah, so I heard some whispers of check if the values are equal. Cool, what would happen if I had this slightly differently and I instead checked if current first is not equal current second? What would this one do instead? Checking the nodes rather than the values. It's always true. Can you compare them? That's a very good question. How would we find out if we could compare them? Try it and see. In this case, what would we expect to happen if we compared them? Let's take a brief tangent. Okay, I'm not going to be foiled by the same mistakes as last time. I'm going to actually comment out my code that has errors in it. Cool, so I've got my first list, my second list. If the head of the first is equal to the head of the second, which is equivalent to saying down here if current first is current second, because they started at the head, then print out they're equal, otherwise print out they're not equal. Yes, it compiled. So who thinks that they're going to be equal? Who thinks that they're not going to be equal? Who didn't raise their hand but wants to raise their hand now? They're not sure, but they just want to raise their hand now. Cool. I appreciate your honesty. So a lot of votes for not equal, a few votes for are equal, a lot of votes for I didn't want to commit to one or the other. Fair enough. So let's run this. This is not what I expected to happen. Wow, I have no idea why that happened. So someone said because they're both pointing to null, but then they'd still be different nodes. here. But the new list should, it's called make list. It's not called new list. I thought I was calling the make list function. I called the new list function. So what just happened there is I thought that I'd made a list like this, and I thought that I'd given values to it. But actually, I just made a list node which pointed to null. And so it effectively had no head. And so because both of them had no first node in them, they were equal. Well, everybody who said yes, looks like you're wrong, looks like I'm wrong. So if I hadn't managed to work that out, one way I could debug that is to actually print out what the values of the pointers are. So %p, you can do, %d for integer, %s for string. You can also do %p for pointer. And so in this one here, what this should tell me is what is the value of the first one? Sorry, what is the address of the first one's head, and what is the address of the second one's head? So if we try this again. There we go. Now that I've successfully made them be different lists, they are not equal. But if I made them be new lists again, they are equal because they both point to null. Cool. I'll just save that code for later, in case you want to look at it again. Yep. Yeah, so that was a good question. When I was comparing the two things, is it the values or just the addresses? In this case, I'm comparing first arrowhead, which is a pointer to a node, so it's going to be a pointer, the address, to second arrowhead, the address of the node, so an address. Cool. Where were we before? Down here. Yeah. Got a syntax error in. Huh, I do. Good spotting. Cool. So looking back at our list SQL one, we do need to compare the values. Because if the values are equal, then the values are the same. The lists contain the same value, or the nodes contain the same value. Checking if the pointers are equal isn't actually going to tell us if the values are the same. Cool. So if the values are not equal, we know the lists are not equal. So what do we want to do here? Yeah, we basically want to say, well, we know they're not equal, so stop now, give up, move along with your life. I'll say it in there, are equal equals false. So I'll optimistically start out by assuming that they're equal, and then I will go, if they're not equal, then say that whether or not they're equal is false. Yeah? Yep, so that's a very good question. When we're doing something like this, when we're testing whether they're equal or not, should we test if they are equal or if they're not equal? So very good question. In this case, I've chosen to check if they're not equal, because if they're not equal, then something interesting happens. We know the lists aren't equal, we've kind of realized something, and so we can make a decision about that. Whereas if they are equal, we don't know if the lists are equal yet, and so we'd have to keep going until they weren't equal at some point. Cool. And so if they are equal, the lists might be equal, so we need to move on. What do we need to put in our else here? I'll hold that thought for a minute. Hold that thought. And so we want to keep going until we hit the end of the list. And the way we move along, so rather than I++, we say Our variable name, or our current pointer is our current pointer's next. Cool. And so, while something, if they're not equal, then are equal is false, otherwise something, and then move along to the next one. So let's think about what is our something going to be? When do we want to stop going through? I can think of two things. So think back to the linked list loops you've done before where you go, stop in a single list when it hits the end. We want to do a similar thing here, right? Oops, well, current first is not equal to null. Cool, so while current first is not null and current second is not null, so the things you want to check are, well, current first is not null, because if it is null, we don't want to keep going, we'll get a null pointer exception, the segmentation fault. If the second one is null, then we want to stop again. And if they're set to equal, then we want to stop as well. So it's like how in other places that aren't this course, you might have seen using break inside a loop. Shh. But rather than using break inside a loop, we can write better code that actually makes a decision, if they're equal, then we want to stop. Cool. Do we need to have anything in here? If the nodes are equal, the lists might be equal. Yeah? The question was, are we allowed to return false here? And then at the end we'd return are equal, I suppose, or true, or whatever it is. I have a question for you. How many returns are there in this function? Is 2 more than 1? So one of the things in the style guide, see, I read a lot of people claimed that they check the style guide all the time, and so I set up something to measure how often people check the style guide. You were lying. You guys don't check it all the time. Although it is a lot of fun watching, what you're doing. So, main function should return, cool. Variables, sure. Function return. The last statement that returns a value must be a return. And aside from the final statement of a function, a return may only be used to exit a function early to handle an error, such as when malloc or a related function returns null. So yes, this translates to you may only return once from a function unless you're handling errors. Good question, and I think we penalized 6 marks in the first assignment for style for that, so do not do that. Cool, and so while the first is not null, the second is not null, and they're equal, if the value of the first one does not equal the value of the second one, then we know they're not equal. Otherwise, something. Yep. Why do I not have to write r equals true? Too many equals there. Yes, that's a very good question. And so, when you say something like, well, I don't know, I is less than 5, this is going to keep on happening as long as this value is to true. So as long as it's true that I is less than 5, it'll keep happening. So rather than saying, like we could write this as while I less than 5 equals true. This would be equivalent, but we don't need to do this because it's implied in the fact that it's a while loop condition or an if statement condition. And so similarly, we could do this, but it's redundant, we can just do this instead. Yep, good question. Cool. Do we need to do anything in here? Seeing one shaken head and a lot of silence, let's just delete it for now. Okay, so set up the current first and second, and assume they're equal for now. If the value of the two nodes at that point are not the same, then they're not equal. and then keep on going until we hit the end of the list, and then return whether or not they're equal. Is this going to work? Who thinks this will definitely work? Who thinks this will probably work? Who thinks this will definitely not work? The tutors didn't raise their hands at all. Clearly the code is fine and not fine simultaneously. Is my code going to work? Thanks for paying attention, guys. So I think it's going to work, but not always going to work. What did you say? It simultaneously will and won't work, so that's why they didn't raise their hand. I see. So let's give it a shot. Int r equal equals, let's equal first, second. If equal else printf, they are not equal. Cool. Let's give this a shot. Compile errors, forgetting to put function prototypes in. One of my greatest skills is forgetting to make prototypes. Let's give that another shot. Cool. So who thinks the two lists that are in fact equal are going to be equal? It was a very enthusiastic thumbs up. Who thinks they're not going to be equal? Who is not paying attention? They are equal. That's good. It's as we expected. What about if we make them not be equal? So if we went something like first, how do I get to the very end? I'm going to just be a bad person and copy this line. Okay, so what about if I make them have a new final node that has the value 17 on one and 18 on the other? So now they shouldn't be equal. And also you can't make a node be equal to an integer. Let's try that again. They're not equal. I heard some people crying out, what about the null on the end? That is a very good point. I intentionally didn't put it there because I just so happen to know that it's going to be put there for us. But actually, let's make that part of this. Node, arrow next, equals null. So now I know that whenever a node is created, its next is going to be null. So we are safe. Cool. So what about if I only added a 17 to the end of one, and I didn't add anything to the end of second? Are they going to be equal? I'll go print list first, print list second. So we can see the first list has a 17 on the end. The second list just has 1, 2, 3, 4, 5. But it said that they are equal. Why could that be happening? Yeah? Yeah, we ended our loop when we got to this null here, so we didn't even consider this 17. And so this comes back to, I don't actually know your names, fantastic idea from before. If the lengths aren't equal, then they can't be equal. The lists can't be equal. And so how could we check that here? We could write ourselves a list length function and go through the list again all the way, but there's an easier thing that we can do. At the end of our loop, we can ask ourselves, were the lists the same size? how would we know if they were the same size? Yeah? Okay, shh. So you suggested having an I and j and increasing them when we increase, but yeah, the problem is we exited it before we hit the end. Yeah? Yep, very good. So if they both point to null, yes, they were. Sorry, the aircon is very cold and my hands are quite laggy at typing. Should have brought some gloves. So if they both point to null, then yes, they were. And if they don't both point to null, then they weren't. So we could just check if current first equals current second. If this is happening, then they both point to null, which means they were equal. But we actually want to check if they weren't equal, even though our thing said they were. So if current first, the thing that current first points to is not the same as current second, then r equals false. We know that they're not equal. Does this make sense? Cool. They are not equal. Very good. So one more quick thing before we have a break. I recommend when you're doing linked list problems and other problems in general, think before you start what are the edge cases. So in the case of this diagram we just drew a diagram for the simple case where the lists were both the same and both the same length. But another good thing to consider is what the possible cases are. So what are the possible cases? We could have empty lists. We could have one empty list and one list that's not empty. We could have lists with one node that are the same and different. We could have lists that are the same length and equal, different lengths and equal, and so on. Or different lengths and equal up until a point. So it's good to think about all of those things in advance. Work out as many of those as you can. Work out how your program would deal with them. Once you've worked all of that out, then start coding. Okay, are there any questions before we take a break? Cool. If you do have any questions, you can ask the army of tutors or me during the break. So let's take a break. I'll make it 12 minutes because then it'll end at 12 past. Timer for 12 minutes. Cool. Do all the usual break things. Stand up, jump around, get a drink, have a nap, whatever you want to do. Hello again, everybody. Hello. Shh. Shh. Hello. Shh. I hope that you had a good break. I've got a couple more linked list things I want to go over. A couple more linked list things I want to go over. And then we're going to look at something really cool called recursion. So, a few more linked list things. Something that your tutors have been telling me some of you have been not thinking about in labs is you need to look out for null. When you allocate memory, that could fail. Maybe there's no memory left on the computer, maybe there's some other reason it's failed, but if you do a malloc or calloc and it returns null and you try to use that, bad things will happen. And similarly, in your functions, your list functions that do things, you could be passed a null pointer. Somebody could pass you a list that's actually null rather than a list. And so, here are some examples. You might make a new node with calloc. What if it fails? Something bad could go wrong, and then if we did new value as 17 after it's failed, something bad will happen. Similarly, if the person who calls some list function passes a null rather than a list, and we try to do this, bad things will happen. And so you've got to make sure that you do something to deal with this. In this case, I've just put a beautiful comment in saying if new is equal to null, then do something. The things you might do here would be if printf to standard error, something went wrong, and exit the program. You might return from the function with some sort of failure status, or use the error function. But do something to deal with it. Think about the fact that it could happen. And similarly, you could be passed a null pointer into your function. So when you make yourself a function, some list function that takes in a list, assert that the list is not null. It is not valid for you to be given a null pointer, but you might be. And if you are, you need to make sure that you don't try and use it. But it's important to know the difference between the list being empty and the list being null. So zoom in on that so it's really big. Make it full screen even. So if the list is null versus the list head being null, one of these is bad and one is a valid case you should consider. Which one is which? Yeah, list head is valid, list is null is invalid, having just said that immediately before. Yes, it's not just invalid, it's bad. So this is something that you need to make sure is not happening in your program, and if it does, you need to kind of quit and go, oh my god, bad things. Whereas if the list head is null, this is a valid case to consider. You might have an empty list. It's possible for your list. Beautiful diagrams here. Here's my list struct, and it points to null. That's a completely valid thing. A list is empty. I mean, when you make a list to start with, it's empty, right? So we need to consider that case. Compared to a list with values in it, so 314 pointing to null. Cool. I'm going to skip over this stuff and go to some interesting stuff. I'll cover this stuff on Wednesday. It'll be fine. You missed out on nothing exciting. What's really exciting is recursion. So first of all, in order to understand recursion, you must first understand recursion. And if you wanted to Google I can't do that in full screen mode. If you search for recursion, Google says, did you mean recursion? Those of you who don't know what this is, don't know what it is, are probably going, what is going on? This is really weird, I'm confused. That's all good. So recursion in C programming is a function that calls itself. And conceptually, recursion is, I'm not really sure how to define it. Let's see what the internet said. Recursion is the repeated application of a recursive procedure or definition. It doesn't really help. Or when a thing is defined in terms of itself, or of its type. I guess if you had a node struct that contained a node struct, which is not really possible because then it would contain itself, and so on. But in C programming, recursion is when a function calls itself. So we could do this. This is a function calling itself. The int do something function with input, and an input could return do something input. What would this code do? Loop forever. Loop forever is not quite the right word, because it's not a loop. It's calling itself recursively. Could crash. I propose we try it and see. Nope. No, that's a bad name. Incidentally, the touch thing in Linux just makes an empty file with that name, which is useful if you want to do this. I'll copy some of this good stuff. What's the date today? 16th. Okay, and so we had a function int do something. I'll make it be void. I'll make it be an int. Do something with some int input, and this is going to call do something with the input it was given. And you suggested I print something out. It's a good point, so I can see what's going on. Okay, and now I'll call do something with our favorite number, 16. And I'm not going to forget my prototype this time. Okay, and so I'm going to call my do something function, and what this function does is it prints out what it was given and then calls the do something function. It doesn't have to return something. I could have made it a void, but yes, I made it an int, so it does have to return something. Do something, no. Do something. I called it bad recursion. Thanks for the warning. It's okay, I know what I'm doing, DCC. Stop telling me what to do, like I totally know what I'm doing. Okay, so is it infinite looping? It's like an infinite loop, except it stopped. Infinite loops don't do that. Yes, ASAN deadly signal. Just to prove that looping forever is different. Oops. Okay, and that should be called loop forever. So start out by looping forever, and then when I'm finished looping forever, I'll do my recursion. God damn it. I've been coding in a language that's not C recently, which doesn't have prototypes. Okay, badge recursion. So this one is going to loop forever, but just to prove it to you, I'll leave it looping forever. So while it loops forever, let's... Yeah, null pointers. So I was asked a really good question during the break, which is, if I have a null pointer and I have another null pointer, do they point to the same thing? Like, is there a null in memory that it can point to? Where is that thing? And to answer that, if we have some int I equals 17, if we wanted to make an int pointer, int star p equals the address of I. As you will hopefully know, this means that p is a variable that contains the address of I. So that might be might be a number like 0xFFFF1234, for example. And so what this means is that p contains an address of something. What about if I made an int star n equals null? We've seen that if I print this out, it says that it's nil in brackets like that, but that's because it's being nice, not because it actually points to the memory address open circle bracket NIL closed circle bracket, since there is no such memory address. So what does a null pointer actually mean? Where does it point to? Does it point somewhere? Is this all a mad conspiracy? To spoil the fun for you, a null pointer, hang on, there we go. Oh no, I think my hand might be too cold to erase things. Oh no, oh no, let's make a new page. So a null pointer, if you printed it out as a number, would have the number 0. What this means, in memory, everything has an address, right? You've got addresses in memory, everything's got a memory address. They range from 0 all the way through to FFFF, which is the biggest number you can fit in a 32-bit number. But memory address 0 is special. Memory address 0 is reserved for being used as a null pointer. There's never going to be anything there. It only exists so that we can say, hey, I've got a null pointer that points to 0. So yes, two null pointers will be equal. They'll both point to the same place, which is 0. I think we've established that this is looping forever. Yep. Can you store anything in a null pointer? So a null pointer is just a pointer that points to 0. You can't store anything in null because it's null. There's nothing that you can't store anything there. You could make a null pointer then point somewhere else and store a value in that, but you can't make it, you can't store anything in null. Yeah. There's nothing except like a void of nothingness and like maybe some dust and stuff. So just for fun, instead of looping forever, let's do something recursively, but this time let's print input plus 1 rather than just input. So what do you think will happen here? Yeah? So you mean 2 strings of the null terminator, or 2 strings? Another very good question. Let's hold that thought, because I want to look at this stuff, but that is a very good question. Think about it, try it. How would you find out? Okay, so now it's, I've called the function, it's calling itself, but each time it's calling itself with 1 more input. And we can see it hit the number 174451. Maybe the 17 is causing problems, who knows? And then we've got this ascend deadly signal. To those of you who'd be coding with GCC at home rather than DCC, I'll run it again with that. We'll see if that does anything differently. Okay, we got a segmentation fault. So you can see that it ran 4 more times, and we got a thing called a segmentation fault. Unfortunately, DCC prevents you from seeing the word segmentation fault, so instead you see ascend deadly signal. But a segmentation fault is something that all C programmers should see and rejoice at or cry because you don't know how to debug your code. But yes, so let's look at the slides. So what's wrong with this? It loops forever. Well, it doesn't loop forever, it recurses forever. But not forever. It stopped and crashed at some point. Wonder why that is. Maybe you should think about it. So the classic, well, one classic example of recursion is factorial. So when we have n factorial, that is equal to itself times n minus 1 times n minus 2 times n minus 3 and so on and so on. So if we had 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1. Someone probably do this faster than me. 5 times 4 is 20. Times 3 is 60 times 2, 120. So 5 factorial is equal to 120. 5 times 4 times 3 times 2 times 1, and so on. So we could calculate this in a loop. Guys, shh. We could calculate this in a loop, right? We could have a loop that goes something like while I is not equal to 0, multiply our current thing by I. So multiplying it by 5, by 4, by 3, by 2, by 1. But we could also write it recursively. Is that on my next slide? That's 2 slides away. So for now, hold this thought. This is a thing that we could do recursively, which we'll see in a moment. Another classic example people use are Fibonacci numbers. How many of you have heard of Fibonacci? Actually, how many of you have not heard of Fibonacci numbers? And are thinking, what is a Fibonacci number? A couple of you. Okay. So the Fibonacci numbers are a famous series, presumably thought up by a guy called Fibonacci, which basically, the nth Fibonacci number something, is equal to the number 1 smaller than it, the Fibonacci number 1 smaller than it, and the Fibonacci number 2 smaller than it. So the best way to draw this is with a diagram. I'm going to call it F to make it easier to write. So F3 is equal to F2, oh no, F2 plus F1. F2 is equal to F1 plus F0. And because we have to stop somewhere, we say that the 0th Fibonacci number is equal to 1, as is the first Fibonacci number. And so in this case, the 3rd Fibonacci number is going to be the 2nd Fibonacci number plus the 1st Fibonacci number. The 2nd one is going to be the 1st one plus the 0th one, and so on. So we can work out what the actual value will be by kind of going back up. Guys, shh. We'll be doing some more coding soon, it's okay. Bear with me for a moment. So The second Fibonacci number is the first plus the 0th, so 1 plus 1. So this here is 2, plus the first Fibonacci number, which is 1. So the third one is going to be 3. What about if we did the fifth Fibonacci number? It's going to be the fourth one plus the third one. The fourth one is going to be the third one plus the second one. The third one's going to be second one plus the first one. That's going to be F2 plus F1. That's going to be F1 and F0. Are you getting bored of me writing this? I'm getting bored of me writing this. Oops, that's 1. So that's 1. We worked out before that F3 was 3. F4 is going to be 3 plus 1, which is 4. It's going to be 7. No, I've gotten it wrong, didn't I? What did I do wrong? Yes, F2 is 2. 8. And so the sequence looks like 1, 1, 2, 3, 5, 8, 13, 8 plus 13, and so on, 21. Cool. And so this is sort of an example of what it looks like broken down and what the numbers look like. And with recursion, we've got to consider two things. First of all, when do we stop? As we saw before, we never stopped, and that was really bad. So we need to work out when to stop. But we also need to work out how to keep going. And recursion is sort of magical. Because unlike coding with loops where you've got to think about what you're doing, with recursion you literally just say, hey, the nth Fibonacci number is the n minus 1th plus the n minus 2th. Guys, shh, magic is happening. So instead of having to write if statements and adding things together in loops and so on, in your code you can literally just write the definition of the Fibonacci sequence, and it will calculate Fibonacci numbers for you. And then the question is when to stop. It's defined Fib0 and Fib1 are defined as being equal to 1. So we know that if we've hit Fibonacci number 0 or 1 that's equal to 1, then 2 is going to be equal to 1 plus 1 and so on. So let's write some code. Here's one I prepared earlier. Cool. So I've set up some code. I've casually forgotten all of these things. This is how you should do recursion. So I've got a function with a prototype called Fibonacci, and this will calculate the nth Fibonacci number. I've got a main function, we'll look at that in a minute. So for the Fibonacci function int n, when do we want to stop as our base case? How do we know when we should stop for the Fibonacci numbers? What do we know about Fibonacci numbers? If n is equal to 0 or n is equal to 1, then we know that it's going to be 1. Right? Otherwise, if it's not going to be 1, then we're going to make be equal to n minus 1 plus Fibonacci n minus 2. So literally, we just write the definition of the thing. The Fibonacci function is this. This is how you get to the next one. This is when you stop. And let's return that. Okay. How many of you, first of all, how many of you are confused? Really? Only like 3 people? I was so confused when I first saw recursion. How many of you think this will work? How many of you think this won't work? Is that because I made a mistake or because you're skeptical that it could work like this? Skeptical that it could work like this? Yeah, me too, right? It's magical. So we have the Fibonacci number we're going to return. If we're getting the 0th or the first one, that's 1, because we've defined as 0, 1 being 1. Otherwise, it's going to be the one before it and the one before that, and return that number. I've written a main function here that just asks you how many you want to calculate and then calculates that many. So let's compile and run this. What? Ah, Yes, they will. Let me try that again. You need an else to go with your if. Cool. Okay, so I want to have the three Fibonacci numbers, the first ones. So the zeroth Fibonacci number is 1, the first one is 1, the second one is 2. What about if I calculate 10? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. How magic is that? We didn't have to do any loops or anything, and it's just magically gone from telling it what a Fibonacci number is to giving us Fibonacci numbers. I can do 20. I can do 30. I can do 40. It's getting a bit slow. What about if I do 50? You can do it, computer. I believe in you. I believe in you. It's getting really slow. Maybe we'll leave this running for a minute. Would it crash if it's too slow? Depends on why it's too slow. Yeah? Do I have to make it a double to deal with the overflow that's about to happen? I think I can get away with a long, because doubles lose precision after a while, or lose accuracy after a while. So for context, what I'm doing here is LLD. Approximately the one after this, it's going to hit something that's negative because it's overflowed the number. Come on, you can do it. Come on, computer. Maybe you should just believe me that the next one is negative. Yeah, there we go. It hit an overflow and I got sad. So I've changed it to be a long, which rather than being 32 bits like an int or 4 bytes, is going to be 64 bits, 8 bytes, which means it can store, I don't actually know how to do the math, significantly larger numbers. And that one should be a long. Need to change my prototype. Hate prototypes. Actually, don't hate prototypes. So I'll compile it with GCC. But then actually I'll compile it with GCC because it'll be faster. Okay, so let's do ourselves. Let's make this a bit wider. I want to calculate 100. Okay, so this is just going to casually calculate the first 100 Fibonacci numbers. How far do you think it'll get by the end of the lecture? You think 50? Does anyone think it'll get to more than 50? Does anyone think it'll get to 100? No. Let's leave that running. I might just sort of tuck that off the screen there because we only need to see what it's up to, not what the number is. It'll need to be wider because I'm going to hit... There we go. And now it's going to flip to the other workspace, I bet. Nope. Okay. Perfect. I'll make this one here a bit narrower. So we can just watch that go. So, why is the Fibonacci slow? Mysteries of the world. Who knows? I know. You might know. Have a think about it. Let's move on. Is there any way that I can make this be full screen and see that still? Probably not. Split screen? Split screen won't do that. I can at least hide the tab bar? No, okay. Would you rather see the slides bigger or the interesting number thing happening? Let's hit 47. Slides bigger? Watching the number? Nobody cares? Okay. It's very exciting. I'm excited. You should be excited. So I'm going to be coding again in a minute anyway. So some things can be a lot easier with recursion. Like we saw there, literally we said, here's the rule for Fibonacci numbers, go and do it. And similarly with linked lists, there are a lot of things that can be that easy as well. We can just tell it, hey, I want to do this thing, here's how you do it, go off and do it. And that's the end of my slides anyway, so there we go, that wasn't a hard question. So I've written a thing for one to get the length of a list. And so, full screen. Cool. And so I'm working with a linked list, so I've copied our skeleton linked list code. I've got the node, the list, the structs, the type defs. I've remembered my prototypes. I've got all my prototypes. It's because I wrote this morning at home and I had more focus. And so I've got some functions, or I will have some functions. One to calculate the length of a list iteratively. So when we say iteratively, or iteration, we mean with a loop. So iterating things is a loop. Recursively is doing a recursive function. If you ever hear the term iterative or iteratively, that means using a loop rather than recursion. And so, did I actually delete? No, it's down here. Okay. So let's write a basic loop to work out the length of a list. Just to see it done this way. How many of you think you could just write this if I said come up here and write it, or write it on your computer so it wasn't scary? How many of you could write the function quite easily to get the length of a list? How many of you couldn't write a function really easily to get the length of a list with a loop? How many of you are not paying attention? At least you're honest. I have another question for you. How many of you could write something to get the length of an array really easily? So they gave you an array. Hang on, no. You know the length of an array. Calculate the sum of an array. Go through every item in the array and add them up. Really easy? Super easy? Super hard? Paying attention? It's fine. So while current is not null, do something and then current equals current arrow next. The do something is going to be get the length. Len starts at 0. Length plus plus. Return len. Cool, hopefully this is all good and hopefully it works. If I comment this out, will it compile? Okay, that should be enough. It's hit 49, that's exciting. I wasn't paying attention to that. You guys should pay attention to that, it's very exciting. Okay. That should just fit. So let's go to COMP1511, week 12, recursion. Yes, it compiles, no prototypes missed. Recursive list length. So the length of the list is 5, but it's not recursive. It's just a loop. We can all do loops. Everything's good. So how do we write it recursively? I'll give you a bit of a hint. In order to get the length of a list recursively, we have to be acting on a node, right? Because if we're going to be calling a function that calls itself and calls itself, we have one list struct, but the rest of the list are nodes. And so we need to have a function that works on nodes, and then a wrapper function that will call this about the list. So this thing here will take in the list, and it will tell us what is the length of the list, starting with the nodes. So return length list arrowhead. And this is because we can't pass a list into it again and again and again, because we have one list and then the rest nodes. So that bit was easy. What about getting the length of a list given nodes? So we need our base case and our recursive case. How do we know when to stop? If we're getting the length of a list, how do we know when to stop? Yeah, when we hit null, exactly. So if node is equal to null, stop. What does stopping mean in this case? What is the length of a list that just contains null? 0? Very good. So if we're at null, the length of this list is 0. We want to stop. Otherwise, if we want to continue with our recursive case, how do we calculate the length of a list? If we look at it like this, we have a list, a series of nodes. What is the length of this list here? What if I said it was the length of this list here plus the length of this list here? So I can say the length of the list is going to be the length of this node, which is 1, plus the length of the rest of the list. And by definition, right, the length of a list is going to be the length of the rest of the nodes plus 1 because the element is 1 long. That's sort of how we could define the length of the list. So it's going to be 1 long plus the length of the rest of the list. And so we've basically defined a way of saying the length of the list. And we can say the length of the list is the length of the list after me plus the node that I am. So this red one would call it like this on the blue one, and then we'd have these nodes here. And so the length of this list would be the length of this one here plus the length of that one there, and so on until it hit null. I will uncomment out this one here. So first of all, who thinks it's going to work? Is that because you understand it or because you blindly trust me to write correct code? It's a foolish choice. You should never trust that anyone will be telling you the truth or will write code that's correct. We've hit 50. It's pretty great. So let's recompile this. Yes, it compiled. Let's rerun it. Recursive list length. The length of the list is 5, and then the length of the list recursively is 5. That's not really very impressive because it's just printed out 5, like maybe I change it. Let's hit 51. Maybe I change it to just print out 5 in the main function without telling you. So let's go in here. The current node is %d. Node arrow value. Probably want to do that at the end so that I'm not dereferencing null. It's still going to dereference null. Okay, so let's go like this. If the node is null, we've hit the end, so print out we've hit the end. Otherwise, the length is what we said before, and print out the current node as the node's value. I had to put that in here because otherwise I'd be dereferencing null if I tried to go node arrow value when node was null. Bad things would have happened. Then I'll print out the length so far. Let's give this a shot. I'll make that a bit wider. Computers are so hard. There we go. So this is what it's done. It's printed out the length of the list is 5, and then we've hit the end. Okay. The length so far is 0. Then we're saying the current node is 5, the length so far is 1. The current node is 4, the length so far is 2. 3, 3, 2, 4, 1, 5. The overall length of the list is 5. So that's a bit weird, it's working backwards. Why is it working backwards? Yeah, exactly, it's got to go all the way through and then I can't whistle as well as you did. So I'll sort of try and draw a diagram of that. I'll make it a smaller list. So if we have this list here, we have some nodes, and I still can't scroll. Oh man. Computers. We have our list here. I'll put 9, 10, 11. So when I call my function, it's going to start out by going, okay, the length so far, we don't know. If it's null, stop, print out at the end. Otherwise, the length is 1 plus the length of the next one, so me plus the next one, and then print out the current node as this thing here. So what this is going to look like is, this is the start. What are you doing? So we start out by calling it on the 9. So the first call we have the 9 is the node that we've been passed in. And so then we're going to call the function on this section here. So this is 9's error next, which is what we're going to call on it next. So we've gone through here, we've gone, is it null? No, it's not. So the length is 1 plus the length of the next one. So we're going to calculate the length of the next one first, and then print out what the current node is. So then that's going to call the second call. It's going to be calling on the 10 now, right? It's going to look at the 10, and then that's going to look at the 11, pointing to null. And so what this is doing is it's saying, it's hit the 10. The current node that's been passed in is the 10. It's calculating the length is 1 plus the length of the stuff after the node, which is the 11. So then the third thing it's going to do, the 11 points to null. And this is an important thing to get. It's going to call it on everything after 11. In this case, it's null. It is going to be calling it on null because that's when we're going to stop. So in this case, we do have a fourth case wherein we call it on null. But because it's null, we've hit this point here. Our length is 0, so we've hit the end. So we're going to print out we've hit the end. We're going to skip over this else because we've gone into this if. We're going to print out the length so far is. And that's told us the length so far is 0. Then this is going to return back to this function. I'll do that in green. So this function here, we've called this function kind of the fourth one down. This is returned the length of 0. So now we're back in the third call here. We're back in this one with the 3 in front. We've done this one here. We've got the length. It's returned to us 0 from this call plus 1, which is myself. So it's now going to print out the current node is 11. Or 5, because this didn't have those numbers. So in the case of my thing written down here, it's going to now print out the current node as 11, and it's going to return its length, which is 1, back to this function call here. Right, so this function call here, number 2, got through here when it's not null. The length is 1 plus the length of the rest of the list, which it passed in the 11. It's now calculated that. It's going to be 1 plus 1, which is 2. And then it's printed out the current node as the 10. The length so far is 2. Then this is going to return back to this function call here that was up to this point here, which has just been given 2. And so it's going to add 1 to 2 and give 3. It's going to pass this one back up to here, which is going to have, hang on. Oh man, oh, I can erase. I did erase that time, excellent. So this one has passed 0 to here, which has added 1 to it and gotten 1, which has passed 1 to here, which has gotten 2, which is going to pass the 2 to here and get 3. Cool. So does that make sense? I'm getting at least 2 nods, at least 2 people, at least 3 people understand. What did you say? Ah, it's 52. Awesome. I've only got 6 minutes left. It's not going to hit 53. That's very disappointing. So does this make sense? Who is completely confused and goes, I can see that this has worked, I can see Andrew has written code and it worked, but I don't understand why, and I'm really confused and it's all black magic to me and I just don't even. How many of you feel like that? Only 2 people. At least you guys are being honest. It took me so long to understand Recursion, and it took me like several years. To be fair, I learned it before I'd learned proper programming and stuff, but for me this was really confusing and really hard to understand. If you're confused, that's okay. Like, being confused is fine, it's a confusing thing, it's a hard thing to think about. But for some people it's a really easy thing to think about, and that's just how their brains think and solve problems. So if you're confused, don't panic. Never panic as always, everything is great, but also you'll get there. Let's wrap up before the web stream cuts off.